So my name is BRYCE ADELSTEIN LELBACH. I've worked on programming languages and compilers for over a decade now, a good bit over a decade now. I've served as the chair of the standard C++ library evolution group, a role from which I am now happily retired. Turned it over to younger generations who will be giving a talk later at this conference. And that's the group that designs and standardizes the C++ standard library. I work at NVIDIA, where I am a principal architect. I drive our strategy for programming models and languages and C++ compilers and C++ libraries, and also now parts of our Python ecosystem. But today I'm here to teach you about the C++ execution model. This model is fundamentally what makes C++, the C++ language, portable and to some degree relevant today. It defines a standard for multi-threaded execution that is broad enough that any platform can implement it, from the smallest DSPs to server CPUs and GPUs. And that is really at the core of what portability means these days. It's not about the size of, bytes or whether or not ints are two's complement. Those are all things that have been decided. When it comes to portability, what we care about now is memory models and concurrent execution and having a portable way to write such code across a wide variety of different types of platforms. So to learn about the C++ execution model, we're actually going to read through part of the C++ standard, slightly abridged, and we'll read through it slowly. And through this exploration, we will discover the core concepts and rules and philosophies of the execution model, and we will see how it works in the real world. So at the heart of the C++ execution model is the C++ abstract machine. And the C++ abstract machine is a portable abstraction of your operating system, kernel, and hardware. It's just an idea. It's not an actual thing. There's no VM in C++. It runs on bare metal. It's just a concept, a notion. And a lot of the things that we'll talk about today are just that. They're just concepts and notions. So the abstract machine is the intermediary between your C++ program and the system and implementation that it is run on. So the idea is that you write portable code, and then you want to deploy that code on a diverse range of concrete systems, and maybe with different C++ compiler implementations. So your code gets mapped onto the abstract machine. You write your code, there's these defined semantics from the standard, the defined machine, and then many different platforms implement that abstract machine, from CPUs to GPUs to other types of accelerators, from all different scales, from your cell phone to the world's largest supercomputers. So C++ programs describe operations that are performed on the abstract machine. And C++ implementations define the characteristics of the abstract machine, and this is sometimes called implementation-defined behavior. And they translate operations on the abstract machine into operations on the system. So the abstract machine's model is actually pretty simple. It is a collection of threads executing operations on objects that reside in a flat global memory storage space. And there are two key concepts here. First of all, threads, and second of all, storage. So in C++, storage is flat. There is no notion of hierarchy, caches, heterogeneous memory, distributed memory, etc. That does not exist as far as C++ is concerned. There's just a flat address space with objects in it. Now, the objects reside in storage at a single memory location. Every byte has a unique address, and no two bytes have the same address. Now, there are some caveats. There are some objects that do not have unique memory locations, like certain types of empty base classes, objects that are marked with no unique address, etc. So an implementation is allowed to store two objects at the same machine address or not store an object at all. So oftentimes we may talk about objects. They may not really be real objects that exist somewhere in memory. They're just, again, a notion. For example, let's say that you have an int, and you never take the address of that int, you never modify it, and its value is a literal. Then the implementation doesn't need to store it in memory because you cannot observe that it is not in memory. If the implementation can prove that, then it doesn't have to put it in memory. So as I said, an object cannot have more than one memory location. If an object could have two different addresses, we would no longer be able to compare object addresses to check for object equality. Consider the self-assignment check in this assignment operator here. And also there are some classes of compiler optimizations that would break down and other ways in which our code might break. So every thread in a program can potentially access every object and function in a program. This is the global part of the address space. There is no notion of things that are private to certain types of threads that cannot be accessed by everyone. Okay. So looking at a diagram of a system, does this type of system meet the constraints of the abstract machine? We have two different processing units. They each have some caches that are not explicitly programmable, but just caches from some main memory. And there's some operating system that puts some virtual memory layer on top of the actual physical memory. And then we have some process that's running in that operating system, and that process has some of that virtual memory allocated to it. So yeah, this meets all of the requirements we just talked about. So how about this system here? We've again got the same operating system and memory layout, but now we've got two different processes, and they both have some process, private memory, but they also have some memory that is shared between them. This is not allowed. This is not within the scope of what the C++ standard considers. So you can do this, but it's just outside of the purview of the standard. And in particular, if you're doing things like using atomics to communicate between different processes, you don't get any guarantees from the C++ standard that will work. You might get that from your platform, but not from standard C++. So no, and there's a few different ways in which this fails. First, the threads in process 0 can't access the objects in process 1, and we just said that one of the rules is all threads must be able to access all objects. Yeah?
Can it done with volatile?
Can this be done with volatile? No. What volatile gives you is an ability to talk to some foreign unknown thing here. But not really with the well-defined sort of semantics that you would want. So volatile does not allow you to have two C++ processes that are communicating with each other through atomics or a mutex or something like that. You would have to do that with guarantees outside of the standard. It may happen to work, but it is not something that's covered by the standard. And there are some cases in which compiler optimizations may interfere with it, or where it may not work on every platform you might want to run on. Now, what if we have a system with two types of processors, each of which has its own distinct memory that is inaccessible to the other, like a CPU and a GPU in a system without some form of unified memory? This is also not allowed. This violates the C++ storage model. We can't have objects that are not globally accessible. All threads must be able to access all objects for us to be able to reason within the constraints of the C++ abstract machine. So for example, if you want to do GPU programming in standard C++, you need a CPU-GPU system that has unified memory where the GPU threads can see all of the CPU thread memory and vice versa. So now, yeah.
What?
And this diagram, virtual memory seems flat. That is correct. That is how most heterogeneous systems work today. There is unified addressing. That's how all GPUs work today. There is universal addressing everywhere. There's a single address system, because it would be madness otherwise. If you could have the same address have different meanings depending on which processor you're on. That does not necessarily mean that there is universal access to memory. Okay, so now let's talk about the primary type of actor in C++, threads of execution. So a thread of execution is a single flow of control in a program which evaluates a function call, and threads may run concurrently. That's the problem. If we just had one, or if they had to run in order, there wouldn't be anything to talk about here. So there's the main thread of execution in a program, which evaluates the main function. That's where everything starts from. Stood thread and stood jthread also create threads of execution, which evaluates the invocable object that is passed to them. And those are actually the only ways today in standard C++ that you can explicitly create a thread of execution. There's a few other ways in which other types of threads of execution may be accessed. This is the only way that you can ensure that you get one created. So now let's talk about how initialization interacts with threads. So variables with static storage duration are initialized as a consequence of program initiation. So that happens prior to the main thread. Variables with thread storage duration are initialized as a consequence of thread execution. So thread storage starts off before you evaluate the thread function of whatever thread you're dealing with, be it main or be it the function you passed into stood thread. And then it's destroyed when that thread, after the evaluation of that function. Yeah. So we have said that threads evaluate a function call. And what does it mean to evaluate a function call? And that is essentially all that C++ does. It just evaluates different function calls. So to understand what evaluating a function call means, we first have to understand what evaluation means. And to understand evaluation, we first have to understand expressions, because that's what evaluation operates on. And so we're going to take a bit of a journey. So an expression is a sequence of operators and operands that specifies a computation. It's like a function call, A plus B, initialization, calling a constructor, stuff like that. Those are expressions. Now, sub-expressions are part of a larger expression. So for example, here we have a statement that declares and initializes a variable of type t. So this contains a number of different sub-expressions. So we have a call to the constructor of t, and then that has some sub-expressions to it, like there's an indirect function call, and then there's a dereference that designates the function that's going to be called by that indirect function call. And then there's expressions that produce the arguments to that function call. Now, full expressions are top-level expressions. They are defined as any expression that is not a sub-expression. Full expressions may include sub-expressions that are not lexically part of the expression, such as the end of a scope, which we'll call destructors, or a function call, which may have default parameters that then become part of the expression. Now, these implicit calls are considered expressions for the purpose of the execution model. Evaluation of an expression includes value computations and the initiation of side effects. So side effects change the environment. They could read a volatile object or modify any object. They could call a library I/O function, or it could be calling a function that does any of the above. Any of these things are considered side effects, the observable parts of a function. So the side effects of A equals A plus B here, depending upon what the assignment operator, well, in this case it's just ints, but it would just be modifying an object here. The side effect of cout A times A here is that we're calling a library I/O function. And this call to foo here, foo A plus B, we don't know what the side effects of that are, but it would be whatever side effects are associated with this function foo. And if we can't see the definition of foo, then we have to assume that it has some side effects. Now, value computations are pure and have no observable effect. The completion of the execution of an evaluation does not imply completion of its side effects. This is very important. I'm going to read it again. The completion of the execution of an evaluation does not imply completion of its side effects. So when we complete evaluating this expression, we finish executing this expression in the language of the C++ standard, that doesn't necessarily mean that the I/O has happened. And likewise, if we had, an assignment to some variable, finishing the execution of that assignment does not mean that the assignment has actually happened. So now we are going to move into the 3 key relationships that tie C++ together and that tie the C++ execution model together. And the first of those is the sequenced before relationship. So given any 2 evaluations, A and B, within the same thread of execution, if A is sequenced before B, then the execution of A shall precede the execution of B. So the sequenced before relationship is asymmetric. If A is sequenced before B, that does not imply that B is sequenced before A. And it's transitive. So if A is sequenced before B and B is sequenced before C, then A is sequenced before C. Oh, that's certainly in the wrong order. So each full expression is sequenced before the next full expression in program order. So here, A would be sequenced before B if they were just statement expressions, or if they were statements, or whatever they would be. This is program order, and that's what sequenced before means. Now, if A and B are indeterminately sequenced, then either A is sequenced before B, or B is sequenced before A, but it is unspecified which. So this means A and B are not interleaved. The execution of A and B is not interleaved. If A and B are unsequenced, then A is not sequenced before B, and B is not sequenced before A, which suggests that A and B may potentially be interleaved. So let's review and look at an example. So if A is sequenced before B, then A executes before B. This is serial execution. As we said, this is what program order means. This is within a thread. Now, if A and B are indeterminately sequenced, then one of them executes before the other, but we don't know which. This is thread parallel execution. So in this case here, the ordering could be AB or BA. It's one of those 2 things. One of them will execute before the other. You just don't know which. Now, if A and B are unsequenced, then their execution may potentially overlap. So this is vector parallel execution. It may also be parallel, but it can also be interleaved. So let's look at an example using C++ 17 execution policies. So here we use the stood execution seek policy, and we've just got a simple for loop here that is doing a vector add. And so stood execution seek guarantees that each iteration is sequenced before the next within the same thread, which is the typical guarantee that you get out of just like basic C++ code here. Right? If you just called this without the execution policy, that's the guarantee that you would get. But we're showing it with the execution policy because we're going to look at some other ones. And so you would get this order on the right here. One thread would do all these things. If we instead use the par execution policy, the iterations may be executed in parallel by multiple different threads, which are colored here. And if we use the unseek policy instead, then the iterations of the loop may be interleaved. You can see here that we've grouped all the loads of y and x together, and then the fused multiply add together, and then the store together. And this is useful because, as you can see, we can then replace those grouped operations together with vectorized operations. Now, in this particular case, we could have done this anyways because there are no side effects from these operations here. So we could not observe if the compiler did this reordering. But otherwise, if you do have side effects and you want the compiler to vectorize, you would need to give it permission to do that with one of these policies that allows the unsequenced ordering. All right, so what about statements? When we're dealing with the C++ execution model, it's best to just think of statements as being compositions of expressions. Everything just boils down to being an expression. So like here, statement 0, whatever that type of statement would be, is going to be sequenced before statement 1. The condition of an if statement would be sequenced before the body of the if statement. And the condition of a while loop is sequenced before each evaluation of the body. There's a bunch of rules that specify all the details of this, but I think you get the basic idea. It happens in program order. So let's talk about operators now and operator evaluation. So the value computations, but not the side effects, of an operator are sequenced before the value computations, but not the side effects of its operands. So the operand expressions to the following operators are sequenced left to right. And then the operand expressions to these operators, to assignment operators, are sequenced right to left. Okay, so now that we understand what expressions are, how expression evaluation works, we can finally talk about functions and how we evaluate functions. And remember that we said earlier that all that a thread does is evaluate functions. So if we understand how functions are evaluated, then we will understand what threads do. Unfortunately, it's a little complicated. So when calling a function, every evaluation within the function and every evaluation not within the function are indeterminately sequenced. The expression designating the function is sequenced before the argument expressions. Each argument expression is indeterminately sequenced with respect to all other argument expressions. There were some changes to this aspect in C++ 17 and attempts to improve this, but this is where we were left. And every expression in the body of the function is sequenced after the expression designating the function in every argument expression of the function. So let's look at an example. Here we've got a function b, which takes two parameters and has a body e. We've got a call to another function g, which takes three parameters, the expression a, an expression containing a call to b, and the expression f. And that call to b takes two parameters, the expressions c and d. Okay, so from that first rule, A and E are indeterminately sequenced, and F and E are indeterminately sequenced. And then we know that B is going to be sequenced before C and D. You evaluate, you figure out what function you're calling before you evaluate any of the arguments to that function, essentially what it's saying. And C and D are indeterminately sequenced. So the arguments to a function will have some ordering, we just don't tell you what. They will not be interleaved. And C and D will be sequenced before the evaluation of E. Which makes sense because we need to evaluate the arguments to a function before we can start evaluating that function. And then A through F are all sequenced before the body of G. Makes sense? We'll look at those rules again. So together, these 4 rules describe the sequencing of our function calls and the expressions within functions. And this ultimately describes the sequencing of our entire program within a thread, as we can just think of our program as being a collection of function call evaluations. So now that we understand the basics of sequencing within a thread, we need to understand 2 more relations to understand how ordering works in C++ in the face of concurrency. The first of those is synchronizes with. So a library operation, and let me say that slide should say something else, but we'll see if that's a problem later. So a library operation A may synchronize with library operations performed by other threads. Synchronizes with is an asymmetric relationship. So A synchronizes with B does not imply that B synchronizes with A. It's a one-way thing. So there are many standard library operations that achieve the synchronizes with relationship, such as atomic acquire and release, mutex lock and unlock, thread create and join, barrier and latch arrive and wait, semaphore acquire release, parallel algorithm fork and join. There's a couple others. So synchronizes with is a runtime relation. You only have it if the operation sees it. So imagine that we have 2 threads communicating data with an atomic flag, which we have here. So the first thread stores to the data and then does an atomic store release to the flag. If the load on the right reads the flag as true, then we have established a synchronizes with relationship between the thread on the left and the thread on the right. But if the load doesn't see the store of true, then we do not have a synchronizes with relationship. Or rather, another way to think of it is if we were spinning in the second thread, you do not have the synchronizes with relationship until you have observed the value that you were the value that was written by the other thread. Simply loading is not enough to establish a synchronizes with relationship. And also, we cannot synchronize from a load to a store. You can only synchronize from a store to a load. So another example, mutex unlock operations synchronize with all subsequent mutex lock operations. So if we have these 3 critical sections and they happen temporally in this order, the unlock that happens at the end of this first one will synchronize with the next lock and actually with all subsequent lock operations that will happen. And now we move on to the most important ordering relationship happens before, which ties together sequencing within a thread and ordering between threads. So given any 2 evaluations, X and Y, if X happens before Y, then either X is sequenced before Y, or X synchronizes with Y, or for some evaluation Z, X happens before Z, and Z happens before Y. So just a transitive property. But the standard goes out of its way to explicitly state it here because it's a very important one. It's very important because the happens before relationship describes arbitrary concatenations of sequenced before, which is ordering within a thread, and synchronizes with, which is ordering between threads. And because all of these relationships are transitive, you can then build chains of ordering from operations within a thread to other threads, and then within those other threads to other threads. So all operations within a thread that are sequenced before a synchronize with will be observable to the other threads participating in the receiving side of that synchronizes with. So now let's revisit an example from earlier to understand this a little bit better. So here, this left thread stores non-atomically to data and then does an atomic store release to the flag. The store to data is sequenced before the atomic store to the flag in that left thread. So the data store, therefore, happens before the flag store. Likewise, the atomic flag load on the right is sequenced before and thus happens before the non-atomic data load. And so thus, if the flag load on the right sees the flag store of true, then it synchronizes with the flag store. And thus, the flag store happens before the flag load. And the data store happens before the flag store. And the flag store happens before the flag load. And the flag load happens before the data load. And therefore, transitively, the data store, the non-atomic data store, happens before the non-atomic data load. And we have a guarantee of memory consistency. So happens before does not mean happened before. That's happens before in, word of power in quotes. If you were able to write a program that witnesses this, then your program would have undefined behavior. Let's look at an example. So here, consider the function foo here. It sets x to y plus 1 and then sets y to 1. The assignment to x is sequenced before the assignment to y. So you might think that therefore it's because it's sequenced before, it would happen before y. And you might think that that means that the assignment to x occurs temporally before the assignment to y. But you are not guaranteed for that to be the case. However, if it was observable, then it would be the case. But in this case, there's no observation here. So if you look at the assembly for code like this with certain compilers, you'll see that the assignment to y may actually be interleaved with the assignment to x here. So here we see we load y into a register, then we store 1 to y, and then we add 1 to the value in the register, and finally then we store that value to x. And there's a few different reasons to do this, like to hide latency. Like, hey, we're loading from memory, that may take a while, and we want to pipeline things because processors execute out of order. Now, again, this only occurs here because the compiler can prove that it's not observable. Now, the rules say the compiler is not allowed to interleave executions of expressions except for in the specific cases that are enumerated. However, we also have this as-if rule that says that the compiler is allowed to make optimizations if they're not observable. In this case, it's not observable. So again, happens before doesn't mean happened before. It happens before relationship doesn't give you a guarantee that X actually occurred in time before Y. It's about observable behavior, not the actual physical behavior in the hardware. Now, a well-defined program is guaranteed to observe things in the happens before ordering, even if that's not what actually happens under the hood. And likewise, happening before doesn't mean happens before, and it doesn't imply that. So X occurring in time before Y does not imply that X happens before Y. And this one's a little bit easier to understand. If in one particular execution of your program, or even if in most executions of your program, X occurs in Y before Y, that is no guarantee that will always happen. Your code may happen to work today, but that does not mean that you have an execution model guarantee of that. And this is important because without a guarantee of that, your program may be susceptible to data races. If you rely on an ordering that's not guaranteed, bad things can happen. What is a data race? Data races start with conflicting operations. Two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. Memory locations are just places where objects live, or parts of objects. The execution of a program contains a data race if it contains two conflicting operations performed by different threads, at least one of which is not atomic, and neither happens before the other. So again, you have to have two conflicting operations. You got to have, if they're both atomic, that's fine. But if one of them is not atomic and you don't have a happens before relationship, then you have a data race. And a data race results in undefined behavior. So consider this program here. We're communicating an int between two threads. The int here is initialized to 0. The producer thread writes 42 to data, and then the consumer thread reads from data and prints it. I think this is pretty clearly bad, but it's important to understand why, by the language of the standard, this is not allowed. Well, we have two different threads performing conflicting operations. They're operating on the same memory location, and at least one of them is performing a non-atomic operation. In this case, both of them are performing a non-atomic operation, and there is no happens before relationship here. We don't see any call to any library facility that would give us synchronizes with operation, and that's what we would need because we're dealing with two different threads. And so we have a data race here, and thus we have undefined behavior. And that means the program could print out 0, it could print out 42, or it could print out any other random integer value. On some platforms, loads and stores might tear, so you might get part of the load or the store. And also, it could print nothing at all. The compiler could decide to delete some of your code here because it notices that there's undefined behavior. Your program could also crash. Lots of bad things could happen because you have undefined behavior. So if we introduce a synchronization primitive, such as a semaphore, you may be wondering, why aren't we using a condition variable here? Because condition variables are horrible and confusing and difficult to program with and very error-prone, and please don't use them. A binary semaphore or a latch or a barrier will suffice for almost all of the circumstances that you might need them. So we're going to use a binary semaphore, which is a new thing from C++ 20, and we're going to get a happens before relationship with it. So what we're going to do is in the producer, we're going to write to data, and then we will do a semaphore release. And then in the consumer, we're going to acquire before we go and load from data. And this will give us the same sort of acquire release semantics that you would get with atomics. It's just with a primitive, an actual OS primitive, the thing that a condition variable ought to be. And so here we're now good because we now have a happens before relationship. So there's no data race anymore. And so this program is going to print out 42. We have a guarantee of that. So we could also use an atomic flag and acquire release semantics to get the same happens before relationship here. And here we're using atomic's wait interface to block until we observe the producer's store. Now it's important to note that we don't get out of a data race here because all operations are atomic, because not all operations are atomic. We've introduced atomic operations to this new thing ready, but we still have a non-atomic store and a non-atomic load of data. And so we still need a happens before relationship. And that's important because if we instead used, say, relaxed loads and stores for the flag, we won't get a happens before relationship between the store and the load because relaxed loads and stores are not synchronization operations. They do not give you an ordering here. And so we would be back to getting undefined behavior. Anything could happen. Now, if we instead make the data itself an atomic and do a relaxed store and a relaxed load, and I should probably say atomic int, not atomic bool. But if we do a relaxed store and a relaxed load here where the data itself is atomic, then we would have a well-defined program. We don't have any happens before relationships here between the threads, but all of the conflicting operations are atomic, so we do not have a data race here. This program will either print 0 or 42, assuming that there's nobody else touching this atomic. We don't know which it will print, but we will get one of those two values. Yes, I just said, yeah, it should be an atomic int. A search and replace mistake, it seems. Okay, so now let's move on to forward progress, which is probably the most complicated part. So first, we have to understand what execution steps are, because that's what forward progress is defined in terms of. So the evaluations executed by threads are delineated by execution steps. And an execution step is termination of a thread, an access of a volatile object, the completion of a library I/O function, a synchronization operation, or an atomic operation. And the completion of an atomic operation would include things like spurious failure here. You may have noticed that this list looks very similar to a list we saw before, which was the list of what a side effect is. And there is a deep relationship between the two here. It's not 100% one-to-one. It's not the case that an execution step is something that produces a side effect, but it's both about what is observable behavior. So a thread of execution makes progress when it performs an execution step or a lock-free execution that does not complete because other threads are making progress. Don't worry about what a lock-free execution is. It's not a talk about the specifics of the memory model per se, but we would need more time than that to get into it. But essentially, this is just saying a thread of execution makes progress when it executes an execution step. As far as we're concerned, that's all we need to know. So some atomic operations may fail spuriously, as I mentioned a moment ago, due to interference from other threads. And implementations are encouraged but not required to prevent spurious failures from indefinitely delaying progress. So on some platforms, like load-locked, store-conditional architectures such as ARM, another thread may repeatedly steal the desired cache line for unrelated purposes in between the load-locked and store-conditional instruction. So on those architectures, something like a weak compare exchange operation may fail spuriously. So even when the atomic object's value is equal to the expected value, it may just fail to complete successfully for a long and potentially indefinite period of time. So to summarize, forward progress guarantees that something observable should eventually happen. I know, it's a very strong promise you get there. Now, implementations may assume that all threads will eventually perform an execution step. So this means that infinite loops that have no observable effects are undefined behavior. This is why your compiler can go and delete an infinite loop from your code. So next, we're going to talk about blocking. This is the slightly more complex part. Now, blocking is defined as waiting for a condition to be satisfied before continuing execution. Blocking library functions are considered to continuously execute execution steps while waiting for their condition to be satisfied, and thus blocking makes progress. So they have to do something to advance forward progress even when they are waiting. We'll talk a little bit later about how they do that. Now, finally, we can talk about the forward progress guarantees, of which there are three. First is concurrent forward progress, in which the thread will make progress regardless of whether other threads are making progress. So examples of concurrent forward progress include preemptive OS scheduling using algorithms such as fair share or round robin, or an unbounded thread pool that will add new OS threads, preemptively scheduled OS threads, to the pool as needed to make progress. Now, parallel forward progress gives you the guarantee that once the thread has executed its first execution step, the thread will make progress. So this is the idea that it will run to completion without being interrupted. So examples of parallel forward progress include tasking frameworks where tasks cannot be interrupted, such as a bounded thread pool, or threads on NVIDIA GPUs. Any other sort of run-to-completion user space tasking system. Finally, we have weakly parallel forward progress, where threads are not guaranteed to make progress at all. So essentially, it's no forward progress guarantee. Now, examples of weakly parallel forward progress include non-preemptive OS thread scheduling, and then tasking frameworks that support task suspension, such as fibers, things like threadless asynchrony, where you can suspend stuff like lazy execution, C++ coroutines, and threads on GPUs not produced by NVIDIA. Get your stuff together, folks. All right, so what guarantees do we get from the main thread? That is implementation defined, which means the implementation will tell you, but there's nothing that the standard says is required of it. And it's the same for stood threads. It is, again, implementation defined. This is fairly important for portability. So on most, platforms, which is your typical, Linux, Mac, Windows, iOS, etc., where you've got an OS and a thread scheduler, you'll get concurrent forward progress guarantees. On some, like if you're on a Linux server that has a certain type of server-centric OS thread scheduler installed, you might only get parallel forward progress because there may be no interruption, no preemption of the threads. On embedded platforms and platforms with no threads, it may be even weaker. You might get, on a platform where there's no notion of threads at all, where it's just a single core executing serially, your main thread would have concurrent forward progress, but your stood threads would have weakly parallel forward progress. Or maybe on that platform, maybe there's some sort of interrupt handler that could come in at any point in time and run an arbitrary amount of code, and then you just get no forward progress guarantee aside from the weak parallel guarantees, even on your main thread. So now we will talk about boost blocking. Boost blocking is when you block on a thread with weaker forward progress while preserving the calling thread's forward progress. So when a thread P boost blocks on a set of other threads, the forward progress guarantees of at least one of the threads in S is temporarily upgraded to P's forward progress guarantee. And this is repeated until the blocking condition is satisfied. And it's unspecified which thread of the threads in the set S are chosen and for which number of execution steps. So boost blocking is a mechanism to ensure that your children threads make progress, but not your siblings. So work that you launch or that you're the caller for. So boost blocking does not protect you from inhibiting the forward progress of non-concurrent threads when using synchronization primitives. So let's work through an example here. Here's a very simple and very bad implementation of a thread pool with a fixed number of workers. So we've got a queue of callables and a mutex. And then we've got this function execute async, which enqueues a callable and returns a shared pointer to an atomic bool, which is a token that we're going to use to track when work is done. And we will wrap the callable we've been given in a lambda, and the lambda will just call the function f, and then it will store true to the token so that we have a way of knowing when this piece of work is done. This is essentially a poor man's future. And then we have a wait function here that takes one of those tokens returned by execute async and waits for it to be ready, just calling atomic wait until that thing is no longer false. So each worker thread in the thread pool will call this process items function, which contains this loop here. And the loop will call trypop, which will lock the mutex, and then checks whether there is work in the queue. And if there is work in the queue, then it will pop a task from the queue, and then it will execute that task. And the tasks in the queue can be thought of as threads of execution with parallel forward progress. We use the term execution agent in the standard for something like this. And once they start executing, they will run to completion on the worker thread. Now, suppose that one of those tasks that's enqueued in this thread pool wants to parallelize the work that it's doing. So it wants to recursively launch more work. And so it spawns some children tasks to process part of the work in parallel. And then it will perform part of the work itself. And then finally, it will wait for the children to complete. And this is where the problem arises, because we said that this is a bounded thread pool. It has a fixed number of OS threads that it has available to execute work. And so, for example, what happens if the thread pool has only one worker serving it? yet we've launched 2 tasks. So the worker will start executing this outer task, which enqueues the 2 children, and then blocks pending their completion. But those children will never complete because there is no worker to execute them, because the worker is executing this function right here that has enqueued them and is now blocking on them. So it is necessary for wait to do something, to boost block, to ensure that forward progress is made. So what we're going to do is we're going to modify wait, and what we need here is we need that any thread that calls wait needs to do something to advance the work in this queue. And the simplest thing that you can do is, instead of just unconditionally waiting on the token for our task here, we can check whether the token is ready in a loop, but then if it's not ready, we'll go and process a work item from the queue. And this donates the forward progress of whoever's calling wait to the work that it is blocking upon. So whatever thread is waiting is going to contribute to processing the work in this queue, ensuring that forward progress occurs. And then with this change, even if we have just 1 thread in the pool, this code will be fine, because we'll start executing this first outer task, and then when we hit the first wait here, instead of blocking forever, we'll execute the first child task, and then that first child task will be done, and then that wait will exit, and then we'll go into the second wait, and then we'll execute the second child task, and then we'll continue. Now, there's other places and ways in which boost blocking comes up. For example, you could do this on the other side. You could do this on the enqueue side. You could say, I want to queue a thread pool where I have 8 threads, and I'm only going to ever put 8 tasks into the queue at once. And if I'm in queuing, and I've got more, and there's already 8 tasks in the queue, or there's already 8 threads that are running something, then I, in the enqueue function, will run whatever the piece of work is. Now, this boost blocking is important, especially on platforms that may have no concurrent forward progress guarantees from their OS threads. The standard library and your code as well may have to do stuff like this to ensure that you have forward progress. All right, so in summary, C++ execution model, basic 1-sentence executive summary is that C++ is threads evaluating expressions that access and modify stuff that's in a flat storage space. And then there's 3 important relationships. Evaluations within a thread is driven by the sequenced before relationship. Interactions between threads is driven by the synchronizes with relationship. And the happens before relationship is this transitive relationship that ties sequenced before and synchronizes with together and allows us to reason about ordering across threads. And then forward progress gives us a promise of eventual termination. So I've made many simplifications. That might be an overstatement, but there have been simplifications, and I've ignored some of the corner cases. The most notable ones is I've completely ignored memory order consume, because we had to change substantially the way in which we describe happens before, and now there's like 3 separate terms for different types of happens before that are only needed to explain consume. Consume's very complicated. Nobody uses it. You don't have to worry about it. You get the basic idea from the model without memory order consume. Also ignored some things related to signal handlers, specifically how signal handlers interact with data races. And there's probably a lot of other things that I didn't feel necessary to mention here, but this is not meant to be exhaustive, to just give you the basic model and idea. If you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast, ADSP, Algorithms plus Data Structures equals Programs. It's available on all streaming platforms. You can go subscribe now. And thank you all for your time and attention. This is a picture my girlfriend took in the Galapagos of blue-footed boobies. They're very cute. I've been putting this in some of my talks.